will continue our discussion with first passage and first return probabilities, how to compute them and so on. So, I just recall quickly that your Fij 0 will be 0, because there cannot be any transition in 0 time. Then Fij 1, that means the first time j is reached from I in one step. So, that will simply be Pij, right. So, the first step transition probabilities are your first time transition probabilities also, and then for the for Fijn we wrote down this formula through which we can recursively compute the Fij. So, you see Fijn will be Pijn minus sigma k varying from 1 to n Fijk into Pjj n minus k. And I had explained last time also that you see we are because Pijn simply gives you the probability of transitioning from I to j in n steps, and it does not, and you in between you could number of times have visited state j. So, all that is included here, because we were computing all possible paths from I to j. So, that may include going to j and then staying over j and so on, and then going from j to somewhere and then coming back to j and all that. So, now we will want to subtract those probabilities from Pijn to compute our Fijn. And so, this says that here this is the first time in k steps you transition from I to j for the first time, and then from j to j in n minus k. So, this again will include going from j and coming back to j, but in between also you can visit j any number of times. So, this Pjj and minus k, and here this is you have already reached j in k steps, and then all this is happening because you are computing the transition probabilities up to n. So, therefore, we have to subtract. So, these particular paths we are subtracting, that means from I to j, suppose you have this, and then you go back here, you come back to j, then again you go back and come back to j and so on. So, n minus k steps you will be doing this, but in k steps you reach j for the first time from I. So, we have to subtract the possibility of traversing all such paths from this one to be able to compute the first passage probabilities. Okay. And so, that is what we are doing. So, I thought that I will revisit this and explain it much better. Okay. Now, we can solve these iteratively from these equations given the initial conditions here. But then we need the Pijn's are available for all n to compute this, right. So, just look at this example again, the job assignment problem, we have p square is this and your F1. So, here we are using the notation that now just as p is the matrix of one step transition probabilities, p square is the matrix of two step transition probabilities, we will also denote the first time first passage transition probabilities as by the matrix F1, then it will be F2 and F3 and so on, right. So, if you want to compute for example, F121, no, what am I doing here? This is F212. Okay. So, you want to compute the probability that you transition from 1 to 2 in 2 steps. Okay. So, this will be by the formula P122 minus F121 P22, right. See here the formula, yes. So, therefore, you reach that means the one step, in one step you go from 1 to 2 and then you have to stay with 2, because there is only one step here, and therefore, if you compute this you get 3 by 16, right. So, now what you see is that you have to so, therefore, now using this formula you can compute, you get the matrix F2. So, you have to compute all 2 step transition probabilities before you can compute the 3 step first passage transition probabilities, and for computing F3 you would need F1, F2 and P3 also. That means, P1, P2, P3, F1, F2 you will need to compute your F3 elements of F3, right. And so, this is lot of work, and so I will give you now alternative method of computing these first passage probabilities without wanting to also without wanting the higher powers of p, just the first transition matrix would be enough. Okay. So, the alternate way, now the alternate way is, see the way we explain this is now look at it as one step. So, Fijn I am writing as sigma k varying from 1 to n p I k. So, you one step you transition right in the beginning, you are starting from I. So, suppose you go to k. So, that probability is p I k, and then from k you can the first step transition probability one I mean first passage transition probability k to j in n minus 1. Is it okay? So, that means k is varying from 1 to n. So, of all possible states you starting from I and you may go to some other k, and then from k you want to go j for the first time. So, here you will require n minus 1. So, you see if you have already computed your f k j n minus 1, then you can compute your f I j n by using the first step transition probabilities, and so this is a neater and more efficient way of computing your f I j n's, right, recursively. So, the argument is okay, right, because I have to move out from I to some this thing, and so k should not be j obviously, right. Because I have to visit j for the first time. So, but then that means I will definitely visit some other state from I to k in one step, since I want to visit j from I in n steps. So, in the first step I will definitely go somewhere which is state which is different from j, and then I need f k j to n minus 1. So, from k to j I should visit j from k for the first time in n minus 1 steps. So, this is a neater way of computing your first passage probabilities. Okay. And now, here we just need the one step transition matrix P, and of course, we are computing these f k j all of these before I compute f I j n, right. And so, here again just doing the same exercise. So, if you want to compute f 232, so then this will be simply p 21. So, remember your k does not have to be, so your k cannot be 3. So, k can take the value 1 and 2. So, therefore, f 21 p 21 f 13 plus p 22 f 23, this is all, right. And so, by taking the values, because this is only p 13. So, this is p 21 p 13 plus p 22 p 23, and you can looking up the values in the matrix P, you get this, right. Now, look at f 312. F 312. So, here your j is 1. So, your k can be 2 and 3. So, this will be p 32 into f 21, right, plus p 33 into f 31, and what is happening is that what is p 32? P 32 is 1 by 4, but then what is f 21? F 21 is p 21. So, p 21 is 0. So, this is 0, then p 33 is 0 into f 31. So, this is 0. So, but then you see, remember, if I have not drawn the diagram here, but if you remember, the path 3 to 1 does not exist, because you did not have the arrow from 2 to 1 in the job transition, this matrix. Yeah, because this is 0. So, you do not have the arc from 2 to 1. So, therefore, this path does not exist. So, anyway, this you cannot transition from 3 to 1 in 2 steps. Okay. First time from 3 to, you cannot reach from 3 to 1 for the first time in 2 steps, okay, in 2 time periods. So, this is definitely better way of computing your f I j n, right. So, now once we know this, then let us talk about the mean first passage times. So, remember n I j we have denoted as the number of transitions that you require for going from I to j for the first time, right. So, then the mean first passage time will be expectation of the random variable n I j, right, which you will write as n varying from 1 to infinity n f I j n. And when you put I equal to j, then it will be m I I, which will be the mean recurrence time, and this we have said is equal to 1 by pi, okay, 1 by pi I. So, the steady state probability of being in, so this is a proportion of time being in state I over the long run. So, 1 by pi I would be the mean recurrence time. So, that will be the time required for reaching. So, on the average this is the time that you will require for reaching from I to I, right, for the first time, right. Now, to compute MIJs, you would need the first passage time distribution. So, you need to compute, you can't apply this formula, right, because you have to then have all f I j n. So, again we will look at a nicer way of computing your mean recurrence time and mean first passage times. So, as we said that to compute Mij by the formula where you need all Fij n up to infinity is not practical. So, let us now come out with another method for computing these mean first passage times. So, you see we will condition on the state at step 1. So, see what happens is if you are computing the mean first passage time, then either the transition from I to j takes in one step. So, then this is 1 into Pij. Remember you are computing the expected value of the Fijn. So, Mij, so if it is one step, then probability of transitioning from I to j in one step, that is Pij. So, 1 into Pij. So, either we will transition from I to j in one step and therefore, 1 into Pij, or we go from I to k in the first step, right, because since it has to be either we transition from I to j in one step, or from I go to some other state, and then from k I will transition back to j. And so, then it will be once I do this, then the passage time becomes 1 plus mkj, because mkj is the mean time of going from k to j, and so 1 plus, because one transition has already taken place. So, the mean time of transitioning from k to j for the first time will be 1 plus mkj, and into the probability of transitioning from I to k, where k is not equal to j. So, this should be clear, right. Okay. Now, we just rewrite this expression, because you see here you are summing with respect to k, and k is not equal to j. So, Pij is missing, which is available from here. So, when you add up Pij plus sigma Pik, k not equal to j. So, this whole thing is the summing up the components of the ith row of the first transition matrix, which must be equal to 1, right, because from I you have to transition to one of the states, and therefore, this is 1 plus sigma mkj into Pik, k not equal to j, and we can rewrite this as summation Pik into mkj, where k is not equal to j. So, this is now again, as I said, the way we computed your formula for Fijn. This is also a simple way of computing your Mij without really wanting to, without really requiring to have the whole distribution for the first passage probabilities Fijn, right. Okay. So, these are n equations in n unknowns. That means n unknowns means in the sense that you are asking for this m to j and so on, m and j. Okay. So, you are asking for first transition passage to j from any one of the states 1 to n. So, these are n variables, and because your I is varying from 1 to n, and then in n unknowns, n equations in n unknowns, right. Now, and similarly we can also compute I can also be obtained this way. So, the first mean first recurrence times can be also obtained by solving the corresponding set of equations here, and let us just work out the formula. This will be so if you want to compute M23, then M23 will be 1 plus, and remember your k is not equal to 3. So, k can take the value 1 and 2. So, it will be P21 into M13 plus P22 into M23. So, now in order to compute M23, I need M13, right. So, I will write down the formula for M13. So, M13 will be, so here again k is not equal to 3. So, this will be 1 plus P11 M13 plus P12 into M23, right. So, then two equations in two unknowns, and we can substituting the probabilities P21, P22, P11 and P12, I get these equations. And so, it is not difficult, because from here you immediately get like half M23 is 1. So, M23 is 2, immediately you get it from here, and then once your M23 is 2, this is half. So, this is 3 by 2, and when you bring this to this side, okay, let us see, M23 is 2. So, this is 1 by 2. So, this is 1 by 2 and this is 3 by 2, and this you bring here. So, that will be half M13 is equal to 3 by 2. Therefore, M13 is 3. It is not just 3 by 2, M13 is 3. Yes, from here. You can again substitute and make sure. So, M13 is 3, this is 3 by 2, and M23 is 2. So, this is what is the mistake? ठीक है, so this is equal to 1 plus M13 we are saying is coming out. So, this is 3 by 2 plus ठीक है, and this is half. So, this is 2 plus 1 3. So, M13. So, therefore, that was the right solution. So, this is M13 is 3. Okay. Yeah. So, working out always helps you, because you can find out your. Now, similarly, let us just look at the way we compute M11. So, the first mean recurrence time for going from state 1 to 1. Okay. And here again your k cannot be equal to 1. So, it will be 1 plus P12 M21 plus P13 M31, and now you need M21 and M31. So, 3 unknowns are there. So, therefore, 3 equations. M21 will be 1 plus again your k is not equal to 1. So, P22 M21 plus P23 M31, and then finally, when you write it down for M31, it will be 1 plus P32 M21 plus P33 M3. And so, substituting for probabilities, I get these equations, and again in a very simple way you can solve, and you can check that. See, M11 comes out to be 5 by 2, and if you remember your calculations for pi 1 was 2 by 5. So, the steady state probability of being in state 1 was 2 by 5, right. So, the mean of first passage time will be 5 by 2. Now, M21 comes out to be 4, and M31 is 2. So, I hope this is a right calculation, because let us see, if you want to do it here, just verify. See, if M21 is 4, then on this side it is 1 plus 2, and your M31 is 2. So, that is also 1. So, that is 4. Yeah, this is coming out to be high, because remember there is no arc from 2 to 1, there is no direct arc from 2 to 1. So, you can of course go from 2 to 3, then 3 to 1 for the first time, but so that is 2, but then other paths when you go around it will be so the mean passage time, first passage time is coming out to be 4, and M31 is 2. Okay. So, now we will see, of course, see the thing is that as I said when I was computing the steady state probabilities and the mean first passage times, there are certain conditions under which these are valid. And so, we now have to look at the situations where these things may not be valid, and in fact, yeah, I had said that these may not even exist and so on. So, we will now start looking at. So, right now under certain conditions which we have to specify, and we will do it soon. So, want to show you that this will be true, all these ways of calculating your steady state probabilities and mean passage first passage times and mean recurrence times. You will be doing it under certain conditions, they are valid, and when they are not valid, then we have other quantities to define those states. So, we will talk about it. So, let us just recall what has been done so far. See, we said that limit probability x n equal to j, given that x naught is I, is actually limit p x n equal to j, and then we defined this as pi j. So, this was the tacit assumption that this limit exists and that it is independent of the initial state, and therefore, we said that you can solve these pi j's through a system of linear equations, right, and that is what we did. So, but this was under the assumption that this limit exists, but now it is not really true that this will always exist, and this is what we need to now talk about and find out. So, therefore, that means our the linear equation method of solving the pi i's depends on whether this limit exists right, and that we said that this limit is also independent of the starting state, and therefore, we could write down the system of linear equations and say that the solution will exist under the condition that sigma pi j's add up to 1, and therefore, things were simple, life was easy, right. So, therefore, we will now look at the conditions under which this limit exists. Okay. Second is that, so the recursive formula for Fijn that we wrote down, this formula is valid. Here we are not asking for any limits or anything, because the powers of p can be computed, and then therefore, through that you can recursively compute your first passage probabilities. So, that is valid, but here and the MIG again, because remember I am saying that the MII's the MII will be equal to 1 upon pi I. So, there again the existence of pi I is assumed, and even otherwise. So, the linear equations for solving your MIJs also needs to be examined under what conditions it will be this method will be valid, right. So, so let us start looking at examples, and then we would want to talk about we start talking about the conditions. So, first suppose so now you again consider the job assignment problem, and you see that the matrix P2 had got all entries positive. In the first transition matrix there were some zeros, in the sense that you were not able to go from 2 to 1, and you did not have a loop from 3 to 3. So, you had 0 entries, but when you took the square of the matrix, then all entries became positive, and after that your P3 was also, all entries were positive, right. So, this implies that there is a path from, remember, because this is simply a transition probability in 2 steps from I to j. So, if it is positive, that means there is a path from each I to each j, and in such a case when you have a path from I to j, right, and then you also have a path from j to I, because Pij2 is positive and Pji2 is also positive, since all entries are positive. So, you have this, you have a path here again from j to I with positive probability, right. Such a pair of states is said to communicate with each other. Okay. So, they are said to communicate, and if all states communicate with each other, and so now because Pij2 is positive for all ij, so we conclude that all states for the job assignment problem communicate with each other, and such a chain or such a Markov chain or process is called ergodic, and we will talk about this some more. So, but first let me say that, so now what we will say is that we will define a closed set as a set of states which communicate with each other, and for the job assignment problem it turns out that your closed set actually consists of all the states 1, 2 and 3, but it is possible that you may have more than 2 closed sets or 3 closed sets, whatever it is. All states may not form one closed set, that means all states may not communicate with each other. And now let us look at this example here. See, this is your transition diagram. So, you see that 1, 2 and 3, you can see that they all communicate with each other. There is a path from 1 to 3, from 3 to 2, 3 to 1 and so on, and there is a path from 4 to 5 and 5 to 4, but there is no path from 1, 2 and 3 to 4 and 5, right. And this you can of course see, the thing is that I have drawn this diagram with 5 states, but when your number of states is large, the transition diagram will be very big, and it may not be, again the same problem as I was talking about earlier, that you can't possibly enumerate all possible paths when you have a large number of states. So, our recourse is to taking higher powers of p. Now, so let us start, and of course, here it is evident that these two, so therefore, your 2 closed sets are 1, 2 and 3 and 4 and 5. So, this chain is definitely not all the states do not form a closed set, right. And so, let us see, let us start with P, the transition matrix. So, you see there is no arc from 1 to 4 or 1 to 5, similarly there is no arc from 2 to 4, 2 to 5 and from 3 to this, right. And same way there is no arc from 3 to 4 to 3, 4 to 1, 4 to 2, 4 to 3 and 5 to 1, 5 to 2 and 5 to 3, there is no arc. So, this is the zeros, and let us see if when we take the second power, that means p square, then these zeros remain intact, these probabilities change, right. These zeros may, like this 0 goes away, but this, and then again when you take p 3 these zeros do not go away, right, and here it becomes. So, therefore, now you can say that for among the states 1, 2 and 3, the closed set 1, 2, 3, now you have path from each node to the other 2 nodes, because these are all positive, right. So, they all communicate. So, it means you need at least 3 transition steps to see that there is a path from each of the nodes 1, 2, 3 to the other 2. And similarly, here this of course quite clear. So, this is also all the probabilities are positive here, and therefore, so and you see that this structure will continue no matter what higher powers you take of p, right. You will continue to have zeros here and zeros here. So, therefore, this is the situation where all the states do not form a single closed set, and in fact, if you have more than one closed set, we call such a chain or a process reducible, right. And if all states form a closed set, one single closed set, then it will be irreducible. So, what we have been talking about so far has been a irreducible chain, and irreducible means that all states will communicate with each other, and therefore, it will also be ergodic. So, but again even this classification is not enough, we need to do it further, and so continue the discussion. So, if a single state forms a class, that means there is only one state in a class, it is called absorbing, because obviously the state is not communicating with any other state, it is just communicating with itself. So, then it is called absorbing. That is, so the once the system enters an absorbing state, it will not come out of it. Yeah. So, we will just look at the examples for all these the kinds of states that we are talking about. Now, from the 5 by 5 matrix of the two closed sets, we just looked at this example in which you had 2 closed sets as formed by the states 1, 2, 3 and the states 4 and 5, right. Remember, there was no communication between the states 4 and 5 and 1, 2 and 3 and vice versa. So, these were 2 closed sets, right. So, now if you look at the submatrix 3 by 3 submatrix, see, because otherwise it is all zeros. This is 3, yeah, it was 0 and 0, right, because there was no communication from 4 to 5. So, in the submatrix, the entry 1 3 was by mistake written as 25 by 36, it should be 19 by 36, because all the rows the elements of any row must add up, for a transition matrix must add up to 1. And so, with 19 by 36, the numbers 1 by 6 plus 11 by 36 plus 19 by 36 add up to 1. So, make that correction, and in P 3 also the same correction has to be made, because this mistake got carried over from P 3 where it was by mistake written as 25 by 36 and not 19 by 36. So, you see that the submatrix itself. So, now the case that we were talking about, that your matrix P n in the limit will converge to where the rows are all identical, sorry, whatever the number states k 1. So, this was pi 1 to pi k and so on. So, all rows were identical. Remember, this is the case we had talked about, but now you see it has no meaning here, right, because the rows, these zeros will remain forever. So, we can't say that the rows will become identical. Well, in the sense that, okay, these 3 rows will become identical, maybe you can say, but then below here you have zeros, right, because again 1, 2, 3, 4 and 5 are not communicating with 1 and 2 and 3. So, you will have zeros here and then you will have some positive entries here. So, therefore, you can't say that the rows will become identical, right. These 3 rows will become identical, exactly, that is what I want to show you, that if you, this is P 3. So, P 3, this is 1 by 6, 5 by 24 and 1 by 8. So, supposedly this number will go up a little, and this number will also go up, because you need 6 by 24 is 1 by 4. No, so you need 1 by 4. Okay. So, supposedly you can see that the numbers are close. Similarly, 11 by 36, 7 by 24 and 1 by 3. So, 1 by 3 is 8 by 24. So, therefore, again the numbers are getting close, and similarly here. So, you see that means these 3 closed states, they themselves will satisfy the condition that the steady state probabilities, you know, you can compute the steady state probabilities, and here it will not matter in which the system started. Okay. But to say that all the rows of the 5 by 5 transition matrix will converge to the same values would not be valid. Okay. Now, again this big example I have taken from Ravindran, Phillips and Solberg, and so this is a 8 by 8 transition matrix, and the diagram I have drawn on the other board. And see, I have written down this matrix, though I am not making use of it right now, but it will be a good exercise for you people also to sit down and try to, if you can write a small, I am sure from MATLAB and so on, if you feed this matrix you can get different powers of the matrix. So, it is not too much of a problem getting higher powers, and then whatever I am saying you can also conclude the same things by looking at higher powers of p. But in any case, if we draw the transition diagram, it will look something like this, right. And I am not writing down the probabilities because they are here, and anyway it will clutter up the diagram. We just need to look at the connections, and whatever I am concluding from that is enough. I do not need the probabilities really, except that this P66 is 1, right. So, fine. So, now if you just glance at this transition diagram, then you will see that 4, 5, 8 are connected, 3, 7 are connected, and you may say that 2 and 6 are connected, right. But then when you go further, you see that there is no arc from 6 to 2, and you at when you reach 6, then the probability of coming back to 6 is 1. So, this is a certain event. So, that means once the system comes to state 6, it just stays there, and so 6 is a absorbing state, right. And so, this is not a closed set, because closed set 2 and 6 should communicate and 6 and 2 communicate. So, there is an arc from 2 to 6, but there is no arc from 6 to 2, right. So, this is not a closed set. So, therefore, you have 2 closed sets which are 4, 5, 8 and 3 and 7, that for sure, because you have an arc from 3 to 7 and 7 to 3, right. Now, 1 and 2 do not figure, therefore, this is not a closed set. So, states 1 and 2 do not figure in any of the closed sets, and such states we define as transient, because see what will happen is that, so first of all they are transient, and since you have more than one state, closed state in the system, therefore, this is a reducible system. Okay. So, that is another thing. Now, thirdly, once the system enters a closed set, suppose for example, it enters state 5 or 4, then you see it will keep hopping among these states only, there is no way of going out, there is no arc which is going out of 4, 5 or 8. So, your system will then for infinite number of times go on hopping among the states 4, 5 and 8, and so such states we will call as recurrent, because they will keep occurring again and again, right. So, the moment a system enters the closed set, then there is no way of going out, right, because if this communicated with any other state, then you would that will also form part of the, for example, if 4 communicated with 1, then this will become a closed set. So, that is not true. So, once you enter a closed set, you cannot get out of it. Okay. And similarly here, if you come to 3, then you will go on going from 3 to 7 or 7 to 3, that is all, you will just go round and round, or because there is no loop here either, there is no loop here. So, you will continue doing it, right. And from here, if you come to 2 and then you go to 6, then you get, just stay put in state 6, you do not get out of it. Okay. So, first of all, now after defining the recurrent state, transient state and an absorbing state, you have the closed sets. What we want to say is that each closed set, if you look at, this itself behaves like now a irreducible Markov chain. So, a sub chain of the whole system which is irreducible, right, ergodic, in the sense that if you just consider this, and similarly if you consider the chain consisting of states 3 and 7, then they together form a irreducible chain, and this is both of them 3 and 7 communicate with each other, right. And so, talk about so further classification is needed. Okay. So, now I will give you another classification of these states in terms of first passage probabilities, and that will also give you a good understanding, and of course, another alternate way of determining whether a state is recurrent or transient or whatever it is. So, now let us define Fi as the probability that starting in state I, the process will sometimes return to state I for the first time, right, because Fii(n) was the probability that it returns to state I from I for the first time in n steps, n transitions. So, now when we add up this from 1 to infinity, this will give us the probability of the system returning to starting from I returning to I for the first time in any number of steps, right. So, all possible. So, therefore, this is will sometimes return to state I, right. So, that is important. So, this is the probability. Now, we say that state I is recurrent if Fi is 1. So, that means there is a positive probability there is a it is a certain event that the system will sometimes return to itself to the state I from which it started. So, if Fi is 1, then it is a certain event, right, but if Fi is less than 1, then it is a transient state, right. And so, now you can interpret this as saying that you see if Fi is 1, that means the system will return. So, starting from I, it will return to itself after some time, and then because it is a Markov process, memoryless, that means the past history is not to be considered, then you will again so the whole process starts fresh, and then you will again go to other states and so on, and then come back again to I. And so, every time you come back, the system starts fresh, and since your Fi is 1, therefore, you will keep coming back to I infinite number of times. So, therefore, the way to characterize this is a recurrent state. That means is that once you come to I, then you will keep coming back to I an infinite number of times. But for a transient state, see what is happening is, since your Fi is less than 1, 1 minus Fi is positive. So, this is the probability that the system will not return to state I. Okay. And so, if this is a positive probability, then we will say that this event will also occur. So, therefore, we want to interpret this as saying that a transient state will be visited only a finite number of times. And so, that will be the difference between a recurrent state and a transient state. So, let us just interpret this. Now, you see if the system is in state I for exactly n periods starting in I, and you are exactly for n periods you or visit the state I again for n periods n times, then the probability of that is Fi raised to n minus 1, right, because Fi is the probability of x returning to state I. So, that into n minus 1, and again these are independent probabilities. So, that is why I am raising it to Fi raised to n minus 1 because of the Markov process, the Markov property, and then it does not come back to itself. So, for what, so I am computing the probability that exactly for n periods it has visited state I starting from I. I mean, this is I am writing down the conditional probability of starting in state I and then visiting it for exactly n times, being in state for n times. So, it already started in state I. So, now it needs to revisit state I n minus 1 times. So, this is the probability of revisiting state I n minus 1 n times starting, and then 1 minus Fi is the probability that it will never come back after that, right. Now, this is, and for n greater than or equal to 1, this is now these are the probabilities from a geometric distribution, if you recall. So, what we are saying is that coming to itself is a failure, and then not coming to itself is a success. Remember, so you are asking for the probability in n trials, you are asking for the well, okay, here this is okay, the best way to say it is that this is not coming to itself. So, that happens once, and then this is coming back to itself n minus n times, or coming back to itself it is n minus 1 because it is starting in I, but it has been in state I for exactly n periods. That is, so there are two different things I am saying. So, therefore, here you are saying revisiting itself n minus 1 times. So, therefore, f I raised to n minus 1. Now, when you want to compute the mean for this distribution, then it will be that means n now varies from 1 to infinity, and you compute the mean, then it will be n times 1 minus f I into f I raised to n minus 1, right. And here you can take 1 minus f I outside. So, sigma n f I n minus 1, and this is a geometric distribution, f I is less than 1. So, this is convergent, and this is the arithmetico geometric series. You should all know how to evaluate it. We have done it in the beginning of this course, and so the sum is 1 upon 1 minus f I whole square, and so divided multiplied by 1 minus f I. So, this is it. So, there is a finite, this is a finite positive number. That means the average of a, you see, if it was to visit itself infinite number of times, the mean will not be finite, but here it is, the mean is finite. So, that means you can again interpret this as saying that the state will not be revisited infinite number of times, only a finite number of times it will be revisited. Okay. Now, another way of characterizing a recurrent state. Yeah. So, you see that we have been trying to talk about the same thing in different ways, and that certainly helps you to understand the things better. So, now let us define I n as 1 if x n is I. That means, if at the nth time the system is in state I and 0 otherwise, right. So, this is a indicator variable, and then if you add up sigma I n from 0 to infinity, this will represent the number of periods that the process was in state I. So, starting from state 0, sorry, from time period 0, the initial time, then this will count the number of times the system was occupying state I, right. And now, if you want to compute this conditional expectation, that is given x naught is I, you want to compute sigma I n and varying from 0 to infinity the expectation. So, I will exchange the summation sign. That means, if this thing is finite, that means if this exists, then obviously I can exchange the expectation. So, this is also convergent, that is all I need to interchange. So, therefore, this is expected value of I n given x naught is I, which but I n is equal to 1 if x n is I. So, therefore, this is probability x n equal to I into 1, right, when you conditional probability of x n given I, given that x naught is I. So, 1 times that you will write down, and this we by our definition is p I raised to n. Yeah. So, therefore, summation and varying from 0 to infinity p I n. So, you want to say that sigma I n varying from 0 to infinity represents the number of periods that the process is in state I. So, now if so, okay, once you have computed this, then a proposition immediately follows. The proposition says that if state I is recurrent, that is, state I is recurrent if this is infinity, right, because this is the expected value, and if our definition is that the recurrent state will keep revisiting itself infinite number of times. So, then the expected value will also be infinite, right. So, therefore, this will be infinity, and for transient this has to be less than infinity, right. So, another way of looking at it. Now, see, interesting outcome from here is that if the number of states is finite, see, that is important, is finite. Okay. So, the number of states is finite, then all states of the process cannot be transient. Okay, sorry, cannot be transient. All states cannot be transient. And why? Because if a transient state can be visited only a finite number of times, and you have finite states, let us say you have the number of states are 1, 2 and k, you have k states. Now, this is if all are transient, so this can only be visited let us say t1 number of times, this can be visited only t2 number of times, and this can be revisited only k number of times, tk number of times, right. And now you take max of t1 plus t1, t2 and tk, take the maximum of this, define this as capital T. And then now when you consider the time t plus 1, t plus 2, what happens? Because all the transient states have already been visited, you can't revisit, but the process has to go on, the process has to be in some state at time t plus 1, t plus 2, right. So, this is a contradiction, because if you have only finite number of states and all are transient, they will all get visited their finite number of times, and after that, beyond that time period, the process is going on. So, where does it go? It has to transit to one of the states. So, therefore, in a finite process we mean finite number of states, all states cannot be transient, right. So, therefore, immediately the question is asked, if the number of states is not finite, then is this possible that all states may be transient? And yes. So, we will also look at an example, and we have already looked at such a process, but we did not really talk about this aspect of the process at that time. So, yes, if there are number of states are infinite, then all the states may be transient.